Okay, so the last section that we're going to cover is section 8.3 on linear systems. So this deals with non-homogeneous linear systems. So just like in the one-dimensional case, we basically have two different methods. We have undetermined coefficients and variation of parameters. So we're going to rely a lot on what you already know about how to find solutions to non-homogeneous just differential equations. Okay, so with undetermined coefficients, basically, if you have this non-homogeneous system, so remember to be non-homogeneous, this f of t is not equal to 0. So if f of t has the exact same type of entries we considered before with undetermined coefficients, so constants, polynomials, exponentials, sines and cosines, or any kind of combination of those, products, multiplication of those, or sums of those, then you can use the method of undetermined coefficients to find the particular solution for the system. So here is an example of this. So here we have, if this is our homogeneous part, this x prime is equal to ax. Here is our f. So notice that our f is made up of a polynomial. So the first thing we have to do is we have to find our homogeneous solutions. So just like we did before, we look at what are our solutions to our homogeneous equation, and then we find our complementary solution, and then we look at the particular solution. Okay, so here's our A. So to find the eigenvalues for our homogeneous system, we look at the determinant of A minus lambda I. So remember what you do is you have 1 minus lambda, you have the diagonal minus lambda. Here's our diagonal minus lambda. The off diagonals are the exact same. We take the determinant of that. So we can multiply these together. That's 1 minus lambda times 1 minus lambda minus 9. Simplify this, you get lambda squared minus 2 lambda minus 8. So finding the eigenvalues for this, we factor it, and we get lambda is 4 and lambda is negative 2. Okay, so to find the eigenvalue for lambda equals 4, again, you set up this equation here where you want to have your a minus lambda I times your k equal to 0. So here's my a minus lambda I, and here's my 0. So this is my augmented form. Plugging in the 4, I have this matrix. Adding these two rows together, the bottom row is going to be 0, and I can take a negative 1/3 times this top row, and so I get this system. So here we have a leading 1 in our k1 spot, we have a 0 in our k2 spot, so k2 is our free variable. We can write this equation as k1 minus k2 equals 0, so k1 is equal to k2. So choosing something easy, we let k2 be 1, and so we have our eigenvector 1, 1, which gives us our solution, our k times e to the lambda, lambda here is 4, e to the 4t. So that's one solution for our homogeneous equation. So looking at our second eigenvalue, lambda equals negative 2. Again, we set up the same system. We plug in negative 2, so we have 3, 3, 0, 3, 3, 0. Subtracting these two, we get zeros in the bottom, and multiplying the top by 1/2, we get this system. So again, a leading 1 in our k1 spot, a 0 in our k2 spot, so k2 is free. k1 plus k2 equals 0, so k1 is equal to negative k2. Again, letting k2 be equal to 1, we have the eigenvector negative 1, 1 when we plug it in here. So this gives us our second solution to our homogeneous part. Here's our eigenvector, e to the lambda t, lambda here is negative 2. So our solution to our homogeneous equation, we have a constant times our x1 plus a constant times our x2. Okay, so now we look at our f of t. So f of t is this negative t squared t plus 5. Notice that none are repeats of our homogeneous system, that it's a polynomial, it doesn't have any exponentials in it. So we don't have to worry about any duplications. So what we're going to do is we're going to basically say that we have to have a polynomial form for our xp. The polynomial form is going to have something times t squared plus something times t plus a constant. Because we have the t squared term, so we have to go all the way up to t squared. And these constants, we need to find what these constants need to be so that when we plug this into our equation, x prime equals ax plus f of t, we get the left-hand side is equal to the right-hand side. So looking at the left-hand side, if we have this as our xp, what is our left-hand side is x prime. So here, when we take the derivative of t squared, we're going to have 2t. So we're going to have 2a2t and 2b2t, so this is this part. Here, when I take the derivative of t, we're just going to have 1, so we have this a1 plus b1, and we take the derivative of constants, we get 0. So this is our xp prime. So now looking at the right-hand side, so here's the right-hand side. We want to plug in our xp. So this is our xp, just kind of put all together. So remember before we had the vector a2 b2 times t squared, a1 b1 times t plus a0 b0 vector. So we just put it into 1. So this way it's easier to actually plug it in here and do the matrix multiplication. So plugging in, I want p prime to be equal to my matrix A times xp plus my f. So I want my left-hand side, my first component of my left-hand side, to equal my first component of my right-hand side. My second component of my left-hand side to be equal to my second component of my right-hand side. So we have to do matrix multiplication. So again, doing this row, this is a column vector. So I have 1 times this whole thing plus 3 times the bottom part. And that gives me what I have on the top here. So 1 times my top one plus 3 times my bottom one. So this is what I get. And then similarly, I had the 3 times my top one plus 1 times my bottom one. So again, 3 times my top plus 1 times my bottom, I get this part. This is what my f was. So now I need to equate this left-hand side to this right-hand side. I can do some more simplification over here. So if I look at my terms for t squared, on the left-hand side I have 0 in my first one. On the right-hand side I have the a2 plus 3b2 minus 2. So that a2 plus 3b2 minus 2 has to be equal to 0 because I don't have any t squareds over here. Similarly, if I look at the t squares on my bottom, I'm going to have none over here, so I'm going to have a 0. Here I have 3a2 plus b2, and that's it. Okay, looking at my t terms, so I'm going to have a 2a2 has to be equal to a1 plus 3b1. And here I have a 2b2 has to be equal to 3a1 plus b1 plus 1. So that's how I get these equations. And then my constant terms, I have to have a1 is equal to a0 plus 3b0. And then b1 is my constant term here, and it's equal to 3a0 plus b0 plus 5. So my t squared equations, my t equations, and my constant equations. So if I look, I try to figure out which order. I have a lot of unknown constants, right? So I have 6 unknowns, and I have to figure out what order to evaluate these in. Well, if I look at my t squared equations, notice that I only have a2 and b2 in these equations. 2 equations, 2 unknowns, so I can solve these by themselves for a2, b2. Now if I look at this one, I have to use my a2 and b2. And so once I know a2 and b2, I could plug it in and I could solve for a1 and b1. So down here, I need my a1 and b1 in order to be able to solve for a0, b0. So I start with the t squared, then I go to my t equation using those values I found from my t squared coefficients, and then I use these values here to find my last ones. Okay, so the t squared terms, all I did is I moved this 2 to the right hand side, so I have this system. So if I multiply the top by -3, just so that I can get things simpler, and then I can add these 2 equations, the a2's will cancel out. I'm going to have -8 b2 is equal to -6, so that gives me b2 is 3/4. Once I have b2, I can plug it in. So a2 is going to be 2 minus 3 times 3/4. So here I just get -1/4. So now look at my t terms. I had these equations for my t terms. So notice I need to plug in my a2 and my b2 here. When I plug in my a2 and b2 and move this 1 to the right hand side, I have this equation in terms of a1 and b1. Again, just simplifying, so I'm going to multiply the top one by -3 so I can add to the bottom one, get rid of my a1s. So I multiply by -3, I have this equation. I add the 2 together, and I'm going to get -8b1 is equal to 4/2, or just 2. So b1 has to be -1/4. So once I have b1, I can go back and I'm just going to put it into, actually I put it into this equation. Yes, so I put it into this equation here. And so when I put it in, I get A1 has to be 1/4. And then finally my constant terms, I use that A1 and B1, plug in, move the 5 to the right hand side, have equations in terms of A0, B0, multiply the top by -3. When I do that, I cancel out my A0s, I get equation for B0, and I can solve for B0, I get B0 is 3/4. Finally plugging back in, I have what my A0 should be. So we found our A2, B2, A1, B1, and A0, B0. So once we have all of those, we actually have our XP. So our solution X is going to be our complementary solution plus our particular solution. This is what we found previously as our complementary solution. Plugging these values in up here, we have our particular solution, so we get our general solution. So undetermined coefficients is the exact same as what we did for the one equation case. The only thing is that there's just lots of, there's potentially lots of coefficients to solve for. So if I look at this one, again, this is another non-homogeneous system. I have an exponential over here, so I can use the method of undetermined coefficients. So using methods from last section, I'm not going to go through finding this again, but basically you find the eigenvalues of your A. I'm going to get my eigenvalues of 1, 2, and 5. I can find eigenvectors for each one of those. I have real distinct eigenvectors, and so I can find the eigenvectors for each one of those, and then I get this linear combination for my complementary case. So notice here that this is e to the 4t. It's not duplicated any place. So it's not duplicated, so my xp is this simple vector times e to the 4t. So I plug it into my system, so I have x prime. So if I take the derivative of this, I'm going to have 4 times this e to the 4t. So here's my 4's. This is my a, this is my xp, and then this is my f. So I need to equate all of these, so do the matrix multiplication and add them together. So when I do this and multiply by here, I'm going to have ae to the 4t plus b to the 4t plus c to the 4t plus e to the 4t all has to be equal to 4ae to the 4t. Similarly, my 4b to the 4t is equal to my second row times this column, so I get 0 here, 2b e to the 4t plus 3c to the 4t minus e to the 4t. So this is this equation. I get similarly the same at the bottom. Okay, so I have these two have to be equal, so I equate coefficients. So the easiest one to look at first is this bottom one, because notice the bottom one, if I equate coefficients, my coefficient for e to the 4t here just involves c. My equation for e to the 4t over here just involves c. So I get 4c has to be 5c plus 2. So that tells me c has to be -2. So looking at the second one, I have 4b has to be equal to 2b plus 3c minus 1. I already know what c is. So if I plug in c here, solve for b, I get b is -7/2. Finally go to my top equation. It requires me knowing b and c. So once I know b and c, I can plug them in, and I just have an equation in a. Solving it, I get a is -3/2. So my particular solution is in the wrong order, so this should actually, the a should be up here, so it should be -3/2, -7/2, -2, e to the 4t. So sorry, this is in the wrong order. I'll fix that. But this is my solution, so here is my complementary solution and my particular solution. Okay, so variation of parameters. So similar to the one equation case, another technique is to use variation of parameters. So this is when that right-hand side doesn't have any of those forms with sines, cosines, exponentials, polynomials. So I'm not going to go through the derivation in 8.3, but basically if you go through the derivation, you get a similar equation to what we had last time, where you have to integrate something. So here I end up having my particular solution is equal to phi times the integral of phi inverse f of t. So this is a matrix inverse. What this phi is as the columns, it has my x1, x2 all the way to xn. So this is the fundamental solution set that I have for my homogeneous equation. So basically my phi is this vector that has as the columns my x1, x2, all the way up to xn. Okay, so if I look at this system, here this is secant t, so I know that I can't use undetermined coefficients. So the first step is to solve the homogeneous system. So again, I look and find my eigenvalues. I have minus lambdas on the diagonal, 0 minus lambda, 0 minus lambda, and these stay the same. So then this is easily lambda squared plus 1, so lambda is a complex value. So here to find the eigenvector, I plug in my negative I. So I plug in my I for my eigenvalue, so I have negative I, negative 1, 1, negative 1. Solve this system. Basically, I switch these two rows, multiply by I get zeros down here. So this gives me that K2 is equal to K1 is equal to K2, where K2 is free. So I get this eigenvector, which, remember, to do this, I need to split up into my real part and my imaginary part. Then I can say this is B1 plus IB2, so I use this B1 and B2 to find my solutions. So remember the solutions are B1 cosine beta t. So remember our beta here is 1, minus B2 sine of beta t. Our alpha is our real part of our eigenvalue, which is 0, so this part is e to the 0 t, which is just 1. So looking at this, I can find my solutions. So here I have 0 cosine plus minus 1 sine, so that gives me this minus sine t. Here I have 1 cosine, no, so sorry, I have 0 yeah, so this gives me my first one. Okay, so my B2, I have 1 cosine plus 0 sine, so that gives me this cosine. And then I have 0 cosine plus 1 sine, so this gives me the sine t. So I can put those into my phi so that I can actually find what my particular solution is. So to calculate phi inverse, it's 1 over the determinant. So the determinant here is minus sine squared minus cosine squared. This is going to be just minus 1. Remember what you do to these entries. I flip the diagonal entries, and then I take the negative of the off diagonal. So this is a simple phi inverse for a 2 by 2 system. So I get this equation. So now I put it into my form for xp, so I have my phi. Here I have the integral of phi inverse times my f of t. So looking at this inside part, I multiply through. So here I'm going to have minus sine times 1 over cosine. That gives me this negative tan t plus 0. Then here I'm going to have cosine times my 1 over cosine. That gives me the 1 plus 0. So if I integrate this, if I rewrite this as minus sine t over cosine t, I can use substitution, and I get that the integral of negative tan t is negative natural log of cosine t. Integral of 1 is just t. And I still have this phi sitting on the outside, so the last step is to multiply through. So I have this negative times the negative natural log, so I get sine t natural log cosine t plus t cosine t. Second row times my column, I get this. So that's my particular solution. Putting it all together, I have my complementary solution plus my particular solution. And that is the end of linear systems. So those are the only techniques we're going to look at. We're not going to actually look at section 8.4, so this is the end of linear systems, which is largely based on all of the concepts that you know from just one equation system.